Log on, tune in, find out. Another good idea from Cambridge.
Andreas Kirsch from Karlsruhe as one of the speakers this morning. Well-known Karlsruhe Institute of Technology now, no longer University of Karlsruhe. And he's well known for many contributions to inverse problems, of course, and one of these is linear sampling and then the factorization method, and he will be talking about this development, which has kind of influenced many of us and led to many papers and investigations, and so we are looking forward to more insight into factorization. Thank you very much for being here.
Yeah, thank you very much, Roland, for this nice introduction. First, I want to thank also the organizers of this workshop that they gave me the opportunity to present the factorization method to you. And right at the beginning, I want to apologize to those who have seen parts of the talk, the pictures, and the quite elementary introduction also to this topic. It's difficult beforehand to prepare a talk for an audience from which you don't know really very much. Yeah, KIT, I have to apologize for that as well. It is not my fault that the University of Karlsruhe changed its name. Karlsruhe Institute of Technology causes a lot of confusion in Germany, because an institute in Germany is part of the university and not now we have institutes in an institute, and in particular those who are not within the university or within KIT, they get really confused there. But as I said, it was not the not our idea. Okay, yesterday afternoon, I expect that you remember Rainer's talk on inverse scattering theory. He gave a very detailed and very good introduction into the field of inverse scattering theory, and I use almost the same notation as he did, so that's kind of easy for you. But I use slightly different scattering models. And now let me see if that works, right? This is a whole course. I'm not sure if I can cover everything, but at least from A to D, and I hope that I can also say something about part E. So first, as it is always the case if you work on inverse problems, if you want to design a good method for solving the inverse problem, then you have to know almost everything, or everything as much as you can, about the direct problem. So the first part will be on the direct scattering problem, and then we turn to the inverse scattering problem, some general statements and features of the inverse scattering problem before we come to the main part of this course, the factorization method. And I will show you a factorization first of the far field operator in the Born approximation and in the general nonlinear case. And then there is a link of the scatterer and the range of an operator. And then part D3 is a very kind of interesting topic in itself, so to speak, and this is purely functional analysis, D3, but kind of elementary in some sense, yeah, only bounded or compact operators, no more difficult things. But this is actually a point where the method fails in many cases, and where we would like to have a really good new idea to step forward and bring the method to other applications. It really depends on a functional analytic argument there in the theorem. Then D4 will be the main result of the factorization method. In principle, it gives you an explicit formula for the characteristic function of the scattering obstacle. This is what the factorization method does. And then I will briefly, just one page, show you the connection between the factorization method and the linear sampling method, and also the connection to time reversal. Time reversal is, we figured that out, it's very easy to see, but it took a while, really very closely connected to the factorization method actually. And show you some numerical simulation then. Then part E comes up in the actually here in the far field, if you study the far field operator, if you have a far field operator for the case Rainer Kress studied yesterday, so for the Dirichlet boundary condition on the scatterer, if the waves do not penetrate into the obstacle and you have Dirichlet boundary condition, then the eigenvalue problem, which are linked to the far field operator, are just the eigenvalues of the Laplacian or minus Laplacian with respect to Dirichlet boundary conditions on the inside of D. So that is a classical eigenvalue problem. And in the case of a penetrable obstacle, then you end up and you come up with a kind of strange or new eigenvalue problem, which is a system of functions there, and that is the interior transmission eigenvalue problem. And I will say something about that. And if time allows at the very end, I will also show you that the factorization method can also be done for the impedance tomography problem. Okay, so let me start with a very simple picture. That's a general scattering problem. You have an incident wave. My notation will be U inc. And you have a scattering obstacle or medium, which is with an index of refraction inside of D. And if this would not be present, then this wave would travel forever without being perturbed. But if you have some obstacle or some medium, then this gives rise to a scattered wave, and the total field U is just the sum, the superposition of the incident and the scattered field. Okay, and all the different scattering problems and inverse scattering problems, they are different in the way of how to model wave propagation. And rather than starting with a differential equation, I start with showing you a kind of a plane wave. This is a plane wave depending on x and t, time t and x in space. My presentation first in the introduction will be in R3. So this is a plane wave because this function, or the physical one, is the real part of that. So this is constant if this is constant. So this constant means for fixed t, this is a plane orthogonal to theta hat. My notation is so always if you see a hat there, there's a unit vector theta hat. So now if you bring k, or if you bring that to the other side and divide by k, then you have the kind of a normal form of a plane perpendicular to theta hat, and it travels with speed omega over k in the direction of theta hat. So these are plane waves. And they appeared yesterday in Rainer's talk, of course, as well. And also you have spherical waves. If you have a point, the source point, so to speak, or a point z, and so this would be a spherical wave. Again, the physical wave would be the real part of that. And you see this is constant if this is constant here, and if you bring that to the other side and divide by k, you see that is a sphere centered at z, and the radius is given here with gamma over k and omega over k times t. So if t increases, then the radius increases. So that is a wave, that is a spherical wave, traveling away from the source point, from the point C. Okay, so from now on, we will drop the time dependence e to the minus I omega t. So we study time harmonic problems, just as Rainer Kress did yesterday. And so the functions are all complex valued and depend on x only. Okay, so we start with a very simple scattering model, and I show you the factorization method there. In the simplest case, it is just matrix, something from matrix theory. Okay, so assume you have kind of point sources. You have some points, z1 to zn, different from each other. And so you see here, this part is just a spherical wave traveling away from this point zj, right? And the strength of this spherical wave, of this point source, is proportional to the incident field at that point, Cj. And the constant of proportionality is Qj there. Yeah? Assume for the simplicity it's positive and it's real and positive, right? So here you have just, you added the contributions of each single point, Cj, and just add them up. So it's a simple model because actually if you have a scattering point there, that would influence also the scattering by the next one. But this is suppressed here. I mean, they are just added. No? So then you have the total field is the incident field, and this is the scattered field. Yeah? So this is the point source scattering model. And now we look at the behavior at infinity. How does this sum here behaves for if x tends to infinity? And here again, the notation I use, r is the modulus of x, the vector x, and x hat is the unit vector in the direction of x. No? So r and x hat are the spherical coordinates of the point x. No? And then, yeah, I don't have to do that, of course. If you look at this quantity here, then this, I mean, this is just an identity, trivial identity here. And if you look at these two factors, for x to infinity, that behaves like 1. And here you have to look at the face. I actually carried it out. So this behaves like 1. For r to infinity, that goes away, and x hat is modulus 1. And this part also you can just easily elementary transform that into this. And if r goes to infinity, this goes to 0, this goes to 0. Here you have x hat is 1 plus 1 is 2. That goes away with this 2. So this converges to minus x hat times z. No? So everybody who is doing inverse scattering or scattering has done this kind of calculation once in his life. And so if you do it now, if you do it now for this, for every z, and substitute this here, then you get a common factor. This is a common factor in front of the series, no? And then you get, this is 1, and then you end up with e to the ik minus ik x hat times z here. So this is just, you have this behavior here, the scattered field. This is the common factor there, and here you have this quantity, and that is the first as a term in the asymptotic expansion. Yesterday, Rainer, of course, did that too. So this here is the far field pattern, yeah, of the scattered field, and my notation is u infinity there. I don't, you put infinity down there, I put it up. So you have us is this spherical wave, yeah, with source at 0 times this factor u infinity x hat, no, which this depends only on r, so, and this depends only on x hat plus higher order or lower order terms. And if you in particular have a plane wave of direction theta hat as an incident wave, then you substitute here the plane wave, no, the incident field. This is the incident field then. Yeah, you have to remember e to the ik theta hat is the incidence times zj there. So this is so the far field pattern in this case depends very explicitly on the angle or the direction of observation and the direction of incidence. Okay, now we can formulate in this case a scattering problem, the direct scattering problem. You are given the wave number k and the theta hat, the direction of incidence, the points and the factors, no, the scalars qj, for all j, and you want to determine US and the far field pattern of that. But in this case, the forward problem is trivial. No? The formulas, the solution is given by the above formula. So it happens often, or sometimes at least, that the in many cases, sorry, that the forward problem is simpler than the inverse problem. But here, the forward problem is absolutely trivial, could be analytically solved, and the inverse scattering problem now, that is already in this case an interesting problem. Given the wave number k and given the far field pattern for all, say all directions x hat and all angles of incidence, no, determine the points, no, where the points of singularity, these are singular at that point, and also the factors qj. And more realistic, of course, you are given kind of angles, eta hat to eta n, my capital N is, of course, much larger than the small n. I mean, capital N is larger than the small n. The small n is a number of sources, and the capital N is a number of incident waves, and also the same of that is the angles of incidence, and these are the angles of observation. Okay, and so given a matrix, the matrix now, LM is an n cross n matrix, a complex matrix. This is the response matrix of the system, and you want to determine the qj and the zj, which appear here and there. So with respect to qj, that is a linear problem, of course. You see, it's a linear combination of the qj. But with respect to the points, zj is a highly nonlinear problem, and that is not so easy to solve that. So we can now, the important observation is the following now. We can write that in matrix form. No? So we can define a matrix C little n times large N by this term here. Then this is the adjoint of H here. And you multiply with qj, that is, we put that into a matrix capital Q as a diagonal matrix where all these Q come in. And then you can write this in this form, and that means you have the matrix F can be written as H star, QH. Okay, so this is so you have this situation here. So this is a factorization. So you have a big matrix, capital N is larger than small n, and so H is this one, and this is Q is a small one, and this is H star is that. Okay. Now, what is the what I'm talking about is what people say it's music, the music algorithm, multiple. Oh, what is it? Okay, I have to look it up later in the second part of the talk. I will tell you that again. So, for any point z, you define this vector in C capital N, which is just the quantities which appear here. E to the minus ik, so eta 1 hat times c up to eta hat n times c. Then you see that H star, which appears here, is just made from the columns of this vector. This is a long vector, and H star is just, if you put in for z, z1 to zn, you get these columns here. And the complex conjugates of that, they lie as a row here in this. This is one. Sure. I mean, this elementary matrix theory here. First of all, simple observation, of course, first semester calculus, or not calculus, linear algebra. If z is one of the points, then this vector is one of the columns here. And then, of course, this vector belongs to the range of H star. The columns of a matrix belong to the range of that. You just take a unit vector, one of the coordinate vectors there. And if Z is not in the, does not belong to these points, but you need more in the finite dimensional case, if these columns are linear independent, then this is not in the range of H star. So you have almost always yeah, Z belongs to one of these points if and only if this vector here belongs to the range of H star. Now, if the rank of H is little n, which is smaller than capital N, then again from elementary matrix theory, the rank of this matrix is little n, right? And the range of that is always contained in that. So then you have, if you have full rank here, then you have that the ranges of H star and the range of F coincide. Again, little exercise from linear algebra. So you have what you have almost always. I mean, you have to have these additional assumption there. Z is one of the points if and only if this vector is in the range of F. And F you know. F, the matrix F you know. You don't know H and Q and H star, of course. You know F. But I mean, always you have that is in the range of F, which is the same as saying that this vector is orthogonal to the null space of F star. Okay, so here I just did a little plot here. What you do is now you choose a basis of the null space of F star, and actually, in my case, you see that F star is the same as F. It's a self-adjoint problem because my Q's are assumed to be real. From F, H star, Q, H, you see F is self-adjoint, but it doesn't matter here. That works also if Q is complex. And then you have this condition here. You take the vectors of the basis elements of the null space times this test vector, and that is 0 if and only if phi z belongs to the range of F, and that is equivalent to saying z belongs to one of the points. So if you plot this series against z, then you should see the points. Yeah? If this is 0, then 1 over this is infinity, or yeah, is infinity. So you get really spikes at that point Cj. So you put a grid on your on the area where you is in R2, of course, no, where you expect these Zj to be, and then you just for every z, it's a very cheap to evaluate this sum, and then you just plot it, and you see the spikes, and here you also these are 4 spikes. Okay. Now we come to the, so this is the, you know, the tools there, and that gives you also the hint how to what the factorization method does. You have an operator, your far field operator F, or in this case it's this matrix, and you have a factorization here, and you have a characterization here. Z belongs to one of these scatterers if and only if this vector belongs to the range of H star. But then you have to say something, what is the range of H star? Can that expressed by F? Because F you know, not H star. And in the finite dimensional case, it's really the same. They coincide. We will see in the infinite dimensional case, in the Hilbert space, this is not the case. You have to replace F by the square root of F. There. Okay, so you have seen the wave equation yesterday and Monday several times, of course. And we look at time harmonic waves. So the physical wave is a real part of U. So I suppress the time dependence in the following, as I did before, and we have the Helmholtz equation instead of the wave equation, where now, we write it now from the beginning in that way. C0 is a background constant speed, k is a wave number again, and then we write this quantity in terms of k square 1 plus q. Q is the relative speed minus 1, so q plus 1 would be the relative speed. So I call q the contrast. If c, the speed, is the background speed, then q is 0, and you just get the Helmholtz equation there, the ordinary. But if q is if c is not c0, then you have a q, and then you have this modified Helmholtz equation there. Again, I recall a plane wave of direction theta hat as given by that, and a spherical wave with source point z is given by this. And here I work in d dimension, pretty general. I'm only interested in 2-dimensional and 3-dimensional case. So you have seen that in D3, this is just with a factor 1 over 4 pi, the fundamental solution of the Helmholtz equation. Rainer used it yesterday, of course, too. And for d equal 2, the fundamental solution is I over 4 times the Hankel functions of first order, and on that. This is a logarithmic singularity, and that has a singularity 1 over r. Okay, so the symbol is the same as Rainer's symbol. No? Capital phi denotes the fundamental solution. Okay, so the direct problem is to determine the scattered and the total field when the wave number k, the incident field, and the contrast q is given. And the inverse scattering problem, you have an incident, the incident field, and the scattered fields are known far away from the medium, and the contrast has to be determined. So this, in Rainer's talk, it was an impenetrable obstacle, so you want to determine the shape of the obstacle. Okay, so this is standard literature on that, book by David Colden and Rainer Kress. My book on inverse problems, that has in the old, in the first edition, the sampling methods and the factorization methods were not known at that time. So, but now just appeared a second edition. I want to make advertisement. So the difference between the first and the second edition is that I just added the factorization method in the chapter on scattering theory, and I added an extra chapter on the factorization method or on impedance tomography also. So these are the two only changes between the first and the second edition of this book. And there are other books on this topic, of course, and I only mention the book by Nedelec, but it's the direct problem here. Okay, now that was the introduction. You got already many tools. Again, I look at the scattering problem here. Now the direct scattering problem, I recall the Helmholtz equation. And now, in order that the scattered waves travel away from the object, from the medium, you have to put a radiation condition that replaces, so to speak, a boundary condition at infinity. And that is the Sommerfeld radiation condition. Also in Rainer's talk, it was mentioned here. Sorry. And we assume now that the wave number k is positive, and the contrast q in my talk is an L-infinity function, is real valued, and support of q in some bounded open set D. So outside this bounded domain D, q is 0, and then this is just the ordinary Helmholtz equation. I don't know why I put the x here and there. It's missing. Okay, so first I recall, because it's so simple, uniqueness. First of all, I assume q is an L-infinity function. So I understand the solution in a variational sense U is in the Sobolev space H1 locally, not such that you know this integration by parts. Green's formula gives you this for all test function with compact support. No? But and this is a uniqueness theorem, and the proof is based on the always two ingredients there, based on lemma of Rehlich, which is, for example, not true if you have scattering by unbounded shapes. No? If you have a periodic scattering problem, for example, then lemma of Rehlich does not hold. And unique continuation, this is not a matter of the scattering obstacle, that is just a property of the differential equation. And we saw yesterday in Gunter's talk that for the full wave equation, this is much more tricky than in this case where we have elliptic differential equations. So the lemma of Rehlich tells you if you have a real and positive k and a solution of the Helmholtz equation outside some ball, then if you take this integral of u square over the sphere of radius r and let r tend to 0, if that is 0, then u has to be 0 outside that. So in other words, that means that's the reason why radio waves exist. No? That they if they cannot decay, u cannot decay faster than in R3 than 1 over r. Because if u decays faster than 1 over r, then u square decays faster than 1 over r square, and the surface area is r square, then this would be 0, and this theorem of lemma tells you then there exists no solution there. No? But of course, as Rainer mentioned it yesterday, but he said Helmholtz equation, but for the Laplace equation, so if k equals 0, then this is not true. You said in your talk Helmholtz equation instead of Laplace equation. I noticed this. And unique continuation is the second tool here. If you have a solution of that equation and it's sufficient to have q and L infinity there, if u is 0 on some open set, then u vanishes everywhere. And now the proof of uniqueness is very easy. You just take Green's theorem. First of all, you take, this is a radiation condition. This tends to 0. The radiation condition tells you that this difference decays faster to 0 than 1 over r. So then if you square that and integrate, this tends to 0. Just the binomial formula gives you this on the right hand side. And you see this is positive, and now you have the imaginary part of this term, and it's pretty clear that you use now Green's theorem to take Green's theorem on this ball, or on the sphere is the volume integral here. So this is Green's first formula here, and if you plug in the differential equation from here, you get that, and the right hand side is real valued. So the imaginary part of this vanishes. So this term vanishes, and here you have positive terms. So you see this tends to 0. In particular, the integral over u square tends to 0, if k is positive, what we assumed. Therefore, this is 0, this tends to 0, and now Rehlich's lemma tells you it's 0 outside this ball. Unique continuation tells you it's 0 everywhere. So this is, because it's so simple, and follow Rainer's advice, every talk should have one proof. This is my proof here. I show you, but yeah, existence is based on, you can prove existence by different methods. I come from the school of Göttingen, Rainer Kress. They use integral equation methods. So I think this is also kind of very nice. And you can use the integral equation methods also if you have only q in L infinity. You don't have to deal with classical solution only. You can also do it with weak solutions. So if you have an L2 potential and you look at the volume potential with this fundamental solution phi you have seen before, then this is the only radiating solution of this. Yeah, I mean, actually, this is a definition of the you can look at that. This is a definition of the fundamental solution, so to speak. Fundamental solution is the one which solves that for the direct delta distribution on the right-hand side. And if you put then this here, then you get that. But you can, I mean, this is proven, can you prove rigorously, also different kind of proofs there possible. I'm not going into that. And now we rewrite this equation, yeah, our equation for the total field. I put k squared q on the other side, so that looks already like this, right? But the total field is not radiating, but the incident field satisfies the homogeneous Helmholtz equation. So if you subtract the Helmholtz equation for the incident, then you see that the scattered field satisfies the same equation like that. And so from this theorem here, it's the only radiating solution. So you see from that theorem that now the scattered field is now k squared times q u phi there. That. And so you have that. If you restrict that to d, then you have an integral equation for the total field u, which appears here and there, and the incident field is on the right-hand side. So this is a Lippmann-Schwinger integral equation. This is because d is bounded. This is a compact operator. You can treat that in L2, for example, this integral equation, and then you have to use that this if u is in L2, first of all, qu is also in L2, but then the result is in it's in H1, and then you can immediately see that this integral equation is uniquely solvable. It's a compact operator, so you have to use Fredholm theorem from uniqueness. Existence follows, and so I think it's a very kind of nice approach, in particular for these kind of problems, to use a boundary, not a boundary, volume integral equation approach. Okay, so our theorem is for every q in L infinity, there exists a unique solution of the direct scattering problem, and the restriction of u solves the Lippmann-Schwinger integral equation. I'm doing that here not only because I want to show you a proof of existence, but also I will use that later on for the Born approximation, because the Born approximation is based on Lippmann-Schwinger integral equation. Okay, here's the Lippmann-Schwinger integral equation, and if you look at the far field behavior of phi, we had that already, yeah, then you see that the scattered field is this factor here, which comes up here. No, we had it for d equals 3, and then u infinity, that is essentially this times the fundamental solution goes into e to the minus ik exact times y. And this factor depends on the dimension, is 1 over 4 pi, because that appears in the fundamental solution, and in 2 dimensions it's a different factor there, depending, I mean, which comes from the Hankel function behavior when the argument goes to infinity. Okay, so also you can, if you have solved the Lippmann-Schwinger integral equation, then you can from there immediately compute the far field pattern. You just plug in the total field here and integrate with respect to y. Okay, again, now so far we considered arbitrary incident field. If you look at a plane wave incident, then this depends again on the angle of observation, and because u depends on the incident field, so on the direction theta hat, you have again that your far field pattern depends on x hat and theta hat. Okay, now my favorite picture here. It's now I must confess, first of all, it's an R2, and second, it's done for the Dirichlet boundary condition and not for the inhomogeneous medium case. But the plots should look the same way for the inhomogeneous medium case. So the inverse scattering problem now is we have the far field pattern again, and you want to have all or information about the contrast function q. Well, that is the inverse scattering problem. And here I have two examples. This is one example and that is one example, but in 2D. So in 2D, this would be an angle, x hat, and theta hat would be an angle from 0 to 2 pi. And here I plotted maybe these color plots. On this axis, it's the first argument, and on this is the second argument. So here is the angle of observation, there is the angle of incidence, and this is the real part, and that is the imaginary part of the far field. So this is one example. You see that these are kind of straight lines, and this is kind of more complicated. And the inverse scattering problem would be, I give you this picture here, and you should give me what Q is. And it would be ideal if you have some kind of Fourier transform or so, which just gives you the Q. So unfortunately, we don't have that. Although Samuli will talk about the same kind of problem later on today. Okay. For people who know a little bit about inverse scattering theory, this is pretty clear on that part. This is the theorem of Karp. If the far field pattern depends only on the angle between incident and observed directions, so it is the function psi, this is the angle between these two actors for all, then Q is radially symmetric. So Q depends only on the distance, on the radial component, and in particular, the support of Q is a ball. Yeah, this follows immediately. If you, it's pretty clear. If you rotate the whole geometry, then you get the same result. So it must be rotational symmetric. But this follows from the uniqueness of this inverse scattering problem. That is one of the, absolutely highlights in inverse scattering theory, I think, in my knowledge. So the far field patterns determine Q uniquely. That is, if you have two Qs, Q1 and Q2, and these are the far field pattern corresponding to Q1 and Q2, if they coincide for all angles of incidence and angles of observation, then Q1 must be equal to Q2. And for D equals 3, this is now more than 23 years ago. To my knowledge, they independently discovered that. Adrian Nachman is here. Alexander Ram and Novikov, what is his first name? Forgot. In the same year, they discovered the uniqueness result, and only rather recently the case D equal 2 has been solved by Buchheim. He will be here next week, I've seen, and will give a talk also. Okay, so now I will, I better stop here. It's a good point, but I will a little bit later on in this morning talk on the reconstruction techniques and then start with the factorization method. Okay, thank you, first of all.
Is there any immediate question we need to join? Otherwise, yeah. Switch speakers.